question 3.14. So the question says, it is known that the connecting rod AB exerts on the crank BC a 2.5 kilonewton force directed down and to the left along the center line of AB. Determine the moment of the force about C. So which means we can first draw our free body diagram this way. Then A, B, C. Then we are told that a force acts along this center line AB. So you can draw our force this way. Right, 2.5. I have to convert the 2.5 kilonewton to SI units. So that's 2500 DT. Then, because of the principle of transmissibility, this is that if a force is acting on a straight line along a rigid body, then it can be taken to act at any point on that straight line and it will have the same effect. Which means these two five force acting here, we can take it to act at A and we can also take it to act at B, and it will have the same effects on this body ABC. So we are going to solve this problem in two ways. We are going to take the force acting at A, we're also going to take it when it is acting at B and compare the results whether we are going to get the same answer. So for this, initially we are going to use it acting at A. So for that, I'm going to draw, so you can write here A. So we're going to take it as acting at point A. So we are going to draw our vertical and horizontal components. Then we are going to look for our theta here. We're also going to draw the distance between these points, 0.088 meters, 0.056 meter. Because initially we were given in millimeter, we have to convert them to meter SI units for our calculation. So same here, 0.042 meter. So in order to get our theta, you can see that theta here is the same thing as the angle between this line and this place here. So because we know the distance here, and we also know the distance here, we can extract this triangle in order to calculate our theta, which also will equal to this theta here. So if we extract that, we're going to have something like this. So we're going to say theta is here. We're going to have here. That's going to be the addition of this point 0.088 and 0.056. It should give us 4, 4, 0.144 meters, and here 0.042. So I'm going to use our calculator. Since we have the opposite or the adjacent points, we are going to use our tan. So that will be theta is equal to 0.144 over 0.042. Then our theta should give us tan, which is 3.74 degrees. So you can write out our horizontal and vertical component as 25 sine 73.74 degrees, 25 cos 73.74 degrees. Then since this is done, we can proceed to calculate our moment, which is R times F. So we can calculate for our vertical components first. So the same thing we are going to do is to look at this. So we are going to calculate our moments now. So we can draw our free body diagram this way: A, B, C. We are going to look at the vertical component acting at A. So we are going to ask ourselves if there is, for this rigid body ABC, if it is nailed at C and we have a force acting vertically at A, in which way is it going to tend to move our body? So we can say that if a force is applied vertically here, we can expect our body to move this way. From this initial position, we can expect it to move this way, then this way, then this way. So which means we can expect our body to move in an anti-clockwise direction, which means our symbol, because moment is positive for anti-clockwise, we are going to write our symbol as positive. Then for our perpendicular distance, like I said, we're going to take a parallel at our point of application and a similar parallel at C. So we take a parallel here and a similar parallel at C. Then we look for the distance between them. But if we look at our question here, we can see that the point of application of A and B is on a straight line, which means the distance between this parallel, there's no distance between this parallel, as they will be on the same straight line. So our parallel distance here has to be 0. So we write out our force 25 sine 73.74. Then we look at our horizontal component. We can draw that also here. A, B, C. Oh God, we can draw it here. A, B, C. So we have a horizontal force acting at this A, in which way is it to tend to move our body. So we can see that, like we said before, this is body ABC, and we have a force acting horizontally along A. So which way is it going to tend to move our body ABC? We can also see that the body will tend to move this way. From this initial position, you can expect it to move this way, then this way, then this way. So you can see that our body will tend to move in an anti-clockwise position also. So I'm going to write out our symbol as positive, because positive is anti-clockwise for movement. So next is going to look for our perpendicular distance. So here I'm going to draw a parallel at A and a similar parallel at C. I look for the distance between them. And if you look at our question here, this distance is given at as 88 millimeter. So that's 0 0.088 meter. So we're going to write out our distance as 0.088. Then we write our force 25 cos 73.74. Then we solve it. Then we should have 0 plus 61.6 Newton meter. So our moment is going to be 61.6 Newton meter. Then we draw the symbol for positive. Because it's positive, we draw anti-clockwise for our moment. So that's 61.6 Newton meter is the moment about the force about C. So like I said, we are going to take a look at it where this force 25 is acting alongside B. Where is acting at B to see if we are going to get the same answer. We will move on to that now. So the same thing is we are going to draw our free body diagram A, B, C. So now we're going to take this force acting here. We're going to draw our vertical and horizontal components. And let's look at the distance between them. That's 0.042 meter. And here is 0.056 meter. And here is 0.088 meter. So since we have calculated our theta before, we can write that as 25 sine 73.74 degrees, 25 cos 73.74 degrees. So we're going to calculate our moment, which is R times F. So we're going to take a look at the vertical component. So we draw our free body diagram again. And the body, the force acting vertically here. And we ask ourselves if our rigid body ABC is in this position and it is nailed at C, and when we force acting vertically downward at B, in which way is it going to move our body ABC? So if we force acting at B, we can expect our body to move in this way with the application of force. As you can see that it will tend to move our body in an anti-clockwise direction, which means that our symbol for this is going to be positive. So write out the symbol positive. Then we are going to look for the perpendicular distance between B and C due to the application of this vertical force. So this vertical force B. So what we do is we take a parallel along the path of the application of force and a similar parallel at C. Then we look for the distance between them. So from our diagram, you can see that the distance between that two positions is I'm going to draw our free body diagram. I'm going to draw a free body diagram here. So here A, B, C. The application of force B. So we're going to ask ourselves if our rigid body is in this position ABC and it is nailed at C, you have a force acting downward at B. We're going to ask ourselves in which way is it going to move our body ABC. So we can expect our body to move in this way with the application of force. So you can see that our body will tend to move in an anti-clockwise position. So our symbol for this is going to be positive, and Our distance is, like we said, we're going to take, to calculate our perpendicular distance, we're going to take a parallel along the application of this force and a similar parallel at C. We'll look for the distance between them. And if we look at our question, we can see that the distance here is 0.042 from here to here. From this parallel here. Distance here is 0.042. That's 0.042. We write that our distance is 0.042. We write that our force 25 side, so the 3.74. Then we look at the vertical component, the horizontal component next. We draw a free body diagram A, B, C. Then we say if the force is acting here, in which way is it going to tend to move our body A, B, C? If it is nailed at C, and we have a force acting horizontally at B. So with this, you can see that if a force is acting horizontally at B, we can expect it to move our body this way. From this initial position, we can expect it to go this way, then next this way, then this way. So we can see here that the application of an horizontal force at B, we tend to move our body ABC in a clockwise direction. So for this, our symbol has to be negative. So we're going to write negative as our symbol. We are going to look for our horizontal, our perpendicular distance. So like I said, we are going to draw a parallel at the application of the force and a similar parallel at C. And we are going to look for the distance between them. So as you can see from here that distance between these two positions is 0.056 here. So I'm going to write out 0.056. I'm going to write it as our distance. I'm going to write our force 25 cos 73.74. So we solve that, we should have the multiplication of this give us 100.8 and minus 39.2. So we do that, we're going to have 61.6 Newton meter. I'm going to write, because it is positive, I'm going to draw our symbol for it anti-clockwise. So you can see that if if you take the force as acting at A, acting at B, we got the same answer of 61.6 Newton meter. So you can see that the principle of transmissibility is also verifiable here.